Good morning, everyone. It's a little bit weird, but at the same time, I think fun that we are all in our rooms, right, teaching each other. It's a nice thing. So I have prepared a presentation for today. We're doing a class in a way together with Oscar and the whole team. Because that's kind of a general class that that we used to do before, actually, because many people will arrive at this point without having maybe considered themselves some important deep questions about what we are doing when it goes into what's actually a computer and what's a microcontroller and why we should learn all those things. The truth, however, is that lately I think the whole FAP Academy and MDF team has done a great job on actually pushing forward some of these ideas. And from the first term seminars to now, I think many of you already, in a way, got in contact with those. So I don't want to repeat that much myself, but I still think it's important that we go over this. I would really encourage anyone who wants to interrupt the session and to open it for discussion, because at the end, I think the problem when we learn such a vast territory as it is, let's say, digital electronics and computing, something that many engineers will stay in class at university for 4 years at least. We concentrate in such an amount of time is that we could easily have, let's say, blurry areas, no? I guess it might happen to you that the more you learn, the more you find yourself that there's something that you don't understand. So it's important that we take advantage of these sessions, which are quite general and not just specifically focus on a small and particular machine or process to actually open discussion for those. So today it's a day that, for example, if many people is wondering what's the difference between an ESP32 on my computer, or why should I use an ATtiny instead of a Raspberry Pi, or why I need to run, or I can run an operative system, what actually is an operative system, or why I need to learn about this thing called bootloaders, and why I need to code in Arduino, where I could code in Python, but what's the difference between Python and C? Why let's say, all these questions, I think that it could easily come to your mind when you start learning what you're doing here in FAP Academy. So I'll try to answer some of them, but I'm really happy if we just interrupt us and explain and share your questions. You could always type them on the chat, but I'm happy also if you just simply start talking, because I mean, I think we could manage it easily. So I'm going to share my screen. Okay. By the way, does anyone know if it's better to do it through a PowerPoint or through a PDF? Any comments on this, Santi or Edu?
No.
Both work, no? So I'll do this. Does this work? Do you see my screen, full screen? Yeah. Perfect. Okay, so we'll start quickly by, I lost my mouse, but just a second, sorry. I need to close this, move this. And again, sorry. So we'll start with this presentation, which I call it How to Make a Computer, okay? And many of the topics I'm going to describe here, you already covered them in previous sessions. So think of it a little bit more as a wrap up or as a way to refresh some ideas that either Edu, Oscar, Santi, and even Neil told you. And of course, interrupt me at any time if you think that what I'm saying is not clear or that it drives you to new questions. So, well, let's think for a moment about why we started to make computers. I mean, of course, as in any modern technology, and even old technology, but I think it's more common in modern technologies as we have much more information about why and when they were built. There's a lot of ways we could start talking about computers and who invented them. But what's clear is that there was a big boom on the history of computers that happened on the Second World War. And this was because for the first time, the world had to process such an amount of information that they had to start thinking about machines to process such information. So you might know that one of the first computers was the Colossus, which was built by the British to actually decode the messages from the Germans. But the importance here is not about the war, not about decoding messages, it's about a machine that actually can process information. So actually, something that we need to think is that we are dealing and designing machines that are able to deal with information. And so we need to understand a little bit more how we think information on a digital world to actually make sense of what a computer is. So for me, it's really important also that we start to think on this idea about computing, not computers, because then we easily tend to isolate things in silos and think that the computer inside your phone is different than the one inside your laptop, that's different than the one inside your Arduino, that's different than the one inside your oven, and that's different than the one inside a car and inside let's say any medical machines that these days is helping people cure the COVID-19. So it's important that we think about the idea of computing, because that also will give us more freedom as designers to actually think let's say, forefront and not just stay with the current mentality of our times, describing what a computer actually is. Because computers could be many things. And I won't go into it today because I'm not an expert, but I mean, for sure, Jonathan, who's also here in the class, could even explain you more about actually what phenomena is happening on biology that we could actually describe in computing terms, as for example, how the DNA does error correction and deals with storing information to replicate ourselves and living beings. So, what I was saying, computers are much more than laptops and servers. And I think at this point, you all get this idea because you see that you have your laptop, but your laptop can also be used to, in fact, write code that then you could load into another computer that's in your desk, like, for example, the ESP32 or an Arduino or any board that you actually play with. And you even learn that you could code in your computer things that then you could put through the internet into servers far away from your computer and run the code there. So at the end, this idea that we could create instructions and put them inside machines that are either in our desk or are far away, and these things will deal with data, will process data and give us an answer, like do something on that data. It's actually, I think, an idea that I guess all of you nowadays embrace. Something that sometimes it's a little bit more harder to understand, and I have to say I'm not an expert here because I'm not an expert on designing silicon chips, but it's that computers are not silicon or binary, that we choose them because they are convenient. I don't want to go too much deep on that, but it's important to understand that this idea that computers work with ones and zeros, we choose them because it's extremely convenient. Why? Because ones and zeros means that we could basically store and manage information inside our machines just by saying if there's information or if there's electricity or there's not electricity, instead of having to deal with multiple levels of voltages, for example. Imagine a computer where, depending on the volts, like if it's 5 volts, 10 volts, 15 volts, that would mean a different state, a different number, to say it in really easy words. We realized that it was by far easier to just keep things in ones and zeros, so electricity and not electricity, and then add a lot of them, because as you might realize, when you count instead of base 10 with base 2, suddenly what happens is that you have to add more elements to the same function, right? But this is still beneficial because it's easy to replicate simple elements rather than to build a single element, which is extremely complex. And I say these kind of things because I don't want you to go too much deep into binary. I mean, we are not here to teach a full computer science career, but it's interesting because you could learn from them and apply it into other projects. A really interesting thing about many of the things you are learning in Fab Academy is that you are looking into one of the fields that evolved the fastest and where much money was in the past, let's say 40 or even 60 years. So you could take learnings from there that you could apply into other fields. Sometimes learnings which is what not to do and sometimes what to do. And for example, this case of binary is an interesting one, as I said, because we choose to decide that to make things complex, sometimes it's better than to make things difficult. So to add a lot of things that do really simple stuff together, and they are just capable of dealing with yes or no or 1 and 0, was much more beneficial than building a super complex thing that could deal with 10 levels, which will be what we'll need to actually design a computer that, instead of dealing with ones and zeros, deals with decimal numbers. And as you know also, that the computer works in binary, it doesn't mean that it could present us the information in digital numbers. The same that a computer working in binary doesn't mean it cannot put images on a screen with full color. And then it comes the second one. We decide to use silicon, and that's important. In the idea also that we keep thinking that silicon and the way we are designing electronics with all these black boxes with many legs around and all these transistors and resistors put in boards and PCBs and then embedded inside plastic or aluminum cases is the only way that we could build a computer. But in fact, if you look at the fundamentals of it, there's many more ways we could do so. I won't go that much into detail today, but you'll see, like, in fact, at the beginning, we start to make computers with bulb and relays, and then we move to silicon just because it was convenient. But this doesn't mean that we cannot rethink the way we are building computers. Likely, with the, let's say, development of synthetic biology, maybe Nuria Conde told you a bit during the Biology Zero class, or Jonathan, we are seeing how people start to think, okay, how we could actually use some of these concepts on top of biological entities. And the goal here is not just the idea of biology, which we could talk a lot about it, but it's the idea that sometimes as designers, we think too much that the technology is defined in a way and we cannot change it. Of course, it's hard to change the technology that's been there for many years, but at least it's important to understand that we are there just because it was convenient and not because it's the only way to do something. In fact, it's important even to understand that computers, they don't even need to be digital. So if you think on computers that started emerging at the beginning of the 20th century, they were fully analog. What's an analog computer? Well, I think a really simple analog computer is an analog watch, an analog clock, like the one that maybe as a kid you used to have. I mean, nowadays we don't use watches anymore, at least as much as before. But you might remember they were inside a few gears that were finely tuned, so they could actually count seconds and hours and minutes. So this is the idea actually that a computer could be built just using analog parts, and that actually a computer, it doesn't need to count with ones and zeros. It could deal with things which are not discrete, with things which are continuous. Later on, we'll talk more about it. But it's important that you keep this idea with you, that even before we came out with this idea of digital that had many advantages, we'll talk later about it, it was even possible to compute, or at least to build a machine that could calculate something. I see many messages coming here. I need to do this because if not, I don't have my mouse. Sorry, I go to the chat. Okay, sorry, because I saw a lot of messages on the chat and I thought maybe it was something important for me. I'll go back to the to my presentation. I just have to do it so because the only way Keynote allows me to move the mouse is to close it. A little bit stupid. And just to finish a little bit this introduction, I think the most important thing here is that learning the color principles, it's a little bit what Edu was telling you, help us to be creative. And I think that's something that a lot of people that we went through Fab Academy, that we went through the Fab Lab Wall could tell. And I guess many of you could tell this even, because if you join Fab Academy, if you join the MDF program, it's actually because you know that going into learning a little bit the bits and bytes inside things, not talk just about electronics, but going inside the details of things also help us to be creative. And I think that's extremely important nowadays. As many people, it's taking that technology, it's taking a single path for granted. That's not true. It's taking that path just because there's an industry behind that tries to find solutions which are convenient, which scale well, and at the end, they generate revenue. So it's important that we look at all these things, not just because we are engineers that we want to be the ones that know the better how to actually improve a code inside an 8090-44 to be neat, scalable, efficient. There's many more ways of looking at these things. So in a way, if I try to summarize everything we said till now, we could say that we could separate computers between analog computers and digital computers. We'll go more in a few minutes on them, but just repeat it once more. The core idea about analog and digital is that, or the world we live in, primarily it's all analog. And why it's analog? Because the table you are sitting in, if you try to measure it, it won't measure exactly 10 centimeters. In fact, you could say it measures, well, 10 is really a small table, but let's say it measures 120 centimeters. If you measure it, you might tell me, Guillermo, it measures 120 centimeters. But then, of course, if you go and you get a tool which can measure this table in a finer way, you might tell me that no, it actually measures 120 centimeters point something. So we could say it measures 1,230 millimeters maybe. And because things actually, even though you try to make them extremely, extremely precise, they are never fitting actually inside a specific scale. They are continuous. Instead, with digital, what we do is that we define a scale. We consider that things are discrete. And discrete means basically that we could put a grid on top of things. And by putting a grid, instead of talking about things which are continuous, we talk about things that are finite in a way. And this is really beneficial because then suddenly we can start talking about things as symbols. And that allows us to build systems which are much more robust. But Neil already told you a lot about this for sure, and we'll talk about this later. So I don't want to confuse you too much, but just to show you a little bit how you build a computer. So we could choose if we are going to build a computer, if we'll make it analog or we'll make it digital. And in the 1920s, it was far easier to build an analog computers because digital computers, they didn't exist. In the 2020s, it's far easier to make it digital because digital tools are much more available. And in general, I will tell you, digital, it's better in the idea that it's easier to build, easier to maintain. However, there's analog, it's amazing. And we always need it because we always need analog to talk to the real world. Okay, a computer could be electronics or could be electromechanical. Electronics means that electricity.
Can I ask a question?
Yeah. Go ahead.
What do you mean by, can you kind of repeat what you mean by making an analog computer?
Yeah, sure. Yeah, that's good. I explain it because we'll talk more about digital, but not about analog. So analog computers were basically computers that existed at least in the first quarter or the first half of the 20th century. That what they were doing is that instead of transforming numbers and other information into symbols, so in ones and zeros, and then computing through that, which is quite a complex process if you think so. That's why it took us a few years to actually manage it. They were simply managing things by establishing relations in the physical world. So, for example, as I said on a clock, a way to actually calculate how many seconds are in a minute is just to have 2 gears, that when 1 gear actually counts 60, then this one will move a bit. No, and that's how a clock works. It's establishing a relation between two proportions. Well, a clock looks like a really simple computer, but if I start having this idea one on top of the other, I could build a system, for example, in this case, based on gears, where I could feed, for example, a question that, for example, could be, how many people is going to die from coronavirus today, and based on other existing information, like, for example, the amount of people which is ill and how fast it's spreading, these gears could actually turn and give me the answer for it. Later on, I could replace these gears by voltages, and instead of counting the amount of turns a gear it's doing, I could measure the voltage. For example, saying that each turn is going to be 1 volt. So if I have 100 volts in my circuit, this means that it's a value 100. So at the end, establishing relations between volts or between counts on gears, I could actually build something that's capable of computing, or at least a machine that's capable of managing information on a specific way. However, nowadays, no one else it's using analog this way anymore. So it's a little bit something from the past. However, analog is still something extremely important, because every time our computers need to deal with the physical world, in a way or another, they need to deal with analog. Because every time that you press a key in your keyboard, or you move your finger on top of the screen of your phone, or you look at the screen, these are actually computers that are controlling signals that are on the analog domain, and that actually they are not perfect. They are not. They needs to be managed, taking into account that there's volts, and it's not just an abstraction as digital is. So in a way, what I'm saying is that analog computers is something from the past, but we cannot forget about analog. Is that helping a bit? I mean, I don't want to go too much on it because it's quite advanced and it's not, let's say, a critical thing right now. But hopefully it solves a little bit some questions. So
Yes,
I was before into electronicals versus electromechanical, and I don't want, again, to go too much on that, but just to help you inspire on that. So computers, they started at the beginning to be electromechanical. This means that even though they could be digital, they actually had moving parts inside that were moving. Imagine a computer built out of relays. It had actually coils that were switching electricity in and off. When we move to electronical, suddenly we don't have moving parts. We have electrons controlling electrons and not electrons controlling actually physical parts that move up and down. But still, we could build a computer which is electromechanical. And binary versus decimal, as I said before, we choose decimal because it's far easier to deal with yes or no, with there's voltage, there's no voltage, rather than dealing with a certain level of voltages or a certain level of turns or a certain level of clicks. And again, the last one, which maybe is the newest one here, because all the other three I already briefed them before, it's about general versus special purpose. A general computer is the idea of a machine where we could load a code into it and could do whatever we want it to do depending on the code. So for example, your computer, it's a full general computer. You could load into it any code you want. In fact, even different operative systems, and you could turn it into a machine for playing videos, to a machine for sending emails, to a machine for actually programming another computer, like when you program the ESP32. And the same goes for your phone. Special purpose computers, we refer to computers which we can code sometimes in a way, but they are much limited to do a single function. You might find these computers, for example, in fact, even inside our normal computers, there are sometimes. These are computers, for example, that do things like real-time processing. For example, these things are changing a bit nowadays, but inside, for example, your TV, sure there is a small computer which is capable of decoding the signals from the digital TV and displaying them on screen, or just encoding and decoding the HDMI that comes through there and turning these into a matrix of pixels. So these computers, even though they could be in a way parameterized, even though they could be programmed, they're specifically designed to do a single thing, really fast and really well. And so it's important to know that these two kinds of computers exist because let's say we are not confused, and we also understand that those other things are also computers. The only thing is that they are special computers or special purpose computers. In fact, at the beginning, when computers started, of course, special purpose computers were more common because it's easier to build something that does one thing well rather than something that you could actually program to do whatever you want. But the true magic of computers, the truly revolutionary thing about computers, it's the idea of general. The idea that actually you could load code into them and make them do things that no one thought they were possible when you build them. And that, I think, it's the core idea that actually made computers so powerful. So in a way, if we think about your laptop or your phone, it's a digital, electronical, binary, general purpose computer. That's because it deals with units which are discrete. We could talk more about it later. It's built with electronical components. There's no moving parts inside your phone. Well, there's a few, maybe we could talk about it later, but not that are dedicated to the primary computing operations. It's binary. It counts in base 2, right? Ones and zeros. In general purpose, because we could run multiple sources of code inside. Another thing, of course, is that Apple might not allow us to do so, but it's a policy decision. It's not, let's say, a technical decision, right? I mean, you cannot create your own operating system for your Apple phone just because someone blocked it, but the processor and let's say the components inside are fully capable of doing so, and computers. So if anyone asks you what your computer is, you can always reply that it's not a Mac, it's not a PC, it's digital, electronic, binary, general purpose computer. Quite a long one. So I keep going through, and please interrupt me as if you have any questions. And don't think we'll be all time like this talking and just on big concepts. I'll finish this soon, and we'll go more into, let's say, the details of chips and data sheets. It's really important to understand that a standardization may help us make things cheaper, faster, and build upon other things or others' work. But that it's not that standardization comes there by default. It's the decision that we take, and this it's basically quite revolutionary right now, because if you look inside any digital gadget, you will see they look all the same. We did the Unpacking Intelligent Machines class at the MDEF, and you could actually take advantage. You are at home these days and just look at any device you have around and open it. You don't need to destroy it. I mean, you could assemble it back again, and you'll see that if you look inside your TV, your phone, your laptop, if you look inside any machine that in a way or another looks with the idea of processing information, even if you look maybe at devices which are cheaper, like an alarm clock nowadays, all the time you'll see the same inside. You'll see a processor, you'll see something that's capable of dealing with processing information that runs a specific code inside. The code could be maybe stored inside the same part. It could be on an external hard drive as in your computer. And actually, what you are doing is that you are reading something from the external wall. Let's say you are playing let's say you are, for example, watching a movie in your TV. So your TV is dealing with something from the real wall. It's dealing with these ones and zero, or these electrical pulses, in fact, coming from the Ethernet cable really fast. It's decoding them, and then it's sending those into a processor that's capable of doing everything that needs to be done to actually decode that feed and putting it into an array of pixels that then it's sent to maybe a piece which is the driver that actually managed the screen of your TV. So at the end, what I'm saying here is that this idea that we have some devices dedicated to input, some devices dedicated to output, and in the middle sitting a computer, either if it is an Intel computer like the one running your laptop, or if it is some other weird chip by Samsung or a specific TV manufacturer, they all actually follow the same architecture and they all follow the same approach. I'm not saying it is good or bad. I'm just saying that the way machines work changed radically. If you do this back 20 years ago and you open, for example, a VCR, a video cassette recorder, you will see that actually there was a full lot of wires and PCBs and chips that were just designed for the specific purpose of playing video cassette recorders. And if you look at a mobile phone from the earliest ages, you will see the same. You will see a bunch of chips that were purely dedicated to do the operations of a phone. Like, for example, one chip will be doing the decoding of the transformation of the voice to a digital domain, so analog to digital converter. One will be encoding the voice into a specific codec that could be sent over an antenna. One chip will be dealing with the antenna. And nowadays, what we see more and more is that all these features are packed inside a single chip that actually, through code, it can be parameterized. It could be reprogrammed to do whatever we want. No, and this basically means two things. So when we open machines nowadays, there's few moving parts. There's few let's say a specific or a domain, a specific purpose electronics, and there's more general purpose electronics inside. Let's say, we'll see later, but you mostly will find just two manufacturers of processors inside all these things, of microcontrollers, let's say, inside all these devices. And just to finish that, of course, the problem is that things get more and more compact and things get let's say, more and more standardized. It happens that when we open machines, always we find the same. So you would say that's good because we could reuse them easily. However, the problem is that the way we are designing things, as you might know, it's not for reusability. So it's getting even harder and harder, even though it might look it's the opposite, to actually open your TV, a DVD player, or your phone and repurpose the components inside to do something new. And what I said before, this wasn't like this 25 years ago, and in a way this is the power, but also not just the power, but also the issues that digital created. No, I mean, imagine before, like, I don't know if any of you did it, but if you will open a video cassette recorder, as it was an electromechanical device, it needs to deal with mechanical things. It was full of motors. You could take it apart and reuse parts to whatever you wanted to build. Nowadays, if you open your Netflix streamer, let's say your Samsung TV, or you open a DVD player from the past already somehow, you'll see there's few parts you could actually reuse, because everything is happening inside of silicon, and the code running inside the silicon parts, it's fully closed source, so there's few to do inside them. Let's talk for a moment, and for sure, like, this has been already covered, but it's always good to refresh, digital versus analog. Digital versus analog, it's this kind of question where, in a way, it looks like really easy to answer, but it could go extremely complex. I'll try to take kind of the easy way, because the complex way, there's a lot of like questions that emerge from it, which are really fundamental on the idea of how we actually deal with information. And there's a specific field which is called information theory that talks about this. So if anyone is interested in knowing actually the field that research the limits of digital in a way, and you might need to look at information theory, who was started by a guy called Claude Shannon in the 1930s, more or less. Neil talks about him because he loved him, and many people love him because, in fact, he's the father of the modern age in a way, at least about the digital age. So if anyone is interested on that, you could go to Claude Shannon, and you'll see a lot. And it's interesting, I think, conceptually, from the philosophical part to look at it. Sorry.
Quick interruption, Guillaume. If anyone is interested, there's a lot of references in the Academy documentation in Barcelona.
Exactly. Thank you, Oscar. So in a way, what I'm saying here is that we tend to look at digital versus analog just as a pure, let's say, a technical issue when we deal with our microcontrollers. But just for you to be aware, there's a whole field of research that covers from science to engineering, but also to philosophy, in what actually information is. And by knowing what information is, how we can encode information, so how we can turn information into symbols, and the limits on storing these, the limits on compression, on compressing this, which is, it's quite interesting, I have to say, at least as a designer, as researchers, to know, because that's the world we live in. And knowing the limits, again, and knowing the details of things help us to be more creative in the solutions that we can propose. The basic example of analog versus digital goes a little bit in the thing I said before about the table, in the idea that this wave you see here in gray, that could be, for example, the sizes of all the tables that we have in the class, or could be the wave while I'm talking, right? Could be my voice moving onto the air. It doesn't have a finite number of elements. Nature is not built on top of a scale. It's not built on top of a grid that defines specific levels of measurements. Of course, you could say, oh, it's limited because atoms, they might have a size. Well, yeah, but it's quite a complex thing. And we even discovered that subatomical particles and that atoms behave in quite complex ways. So we cannot say that the nature that we live in, it's built on top of a grid. But for the convenience of manipulating information, we found that having things in a grid, having things in a discrete manner is actually much more convenient. And you could see here the example, right? We have this gray shape on the screen, and then what we do is that we try to approximate these numbers into the grid that we establish, which is a grid of 8, as you could see. Sorry, of 7. And actually, that's what you could see here is that we are basically just trying to approximate to the closest value. At the end, what this allows us is that instead of having to store this continuous wave, what we are just storing, it's the fixed values where this wave is nearby. However, and that's extremely important, many people could tell you, oh, and so when I encode things into digital, I'm losing a lot of information. because look at the screen, right? It looks like the gray wave, it's much neat. The gray wave is actually representing the reality, and the red square wave, in a way, the red line is actually not showing the reality. It's showing something which a distance a lot from it. Well, it's important to understand that this is just an exaggeration for two reasons that Oscar, in fact, could explain you better, because he knows much more than I do on this field. But there's two important things to know there. If you sample if you sample an analog wave, so if you increase the number of times that you actually draw these vertical red lines, you will end up with a grid that has almost the same resolution as the gray shape. But on top of that, if actually you add some magic on top of it, and I say magic because I don't want to go now into low pass filter and anti-aliasing and a lot of complex features behind transforming analog to digital, we could actually build something that it actually matches at a level which is extremely high. And you all know this is possible because you are designing things in your computer in Rhino, and then you are 3D printing them, and you can measure them with a caliper and they fit. And Rhino deals perfectly on the digital domain. Rhino is not storing exactly the perfect curve there. It's just storing some numbers that represent that curve. And the same while I'm talking to you now. You don't listen my voice just in bup, 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 bup. You listen my voice more or less fully. And the same when you listen to music. And all these processes, they are dealing by basically taking something which is analog and turning it into something which is digital. But again, the importance of doing so is that once they have this grid here, the beauty is that, look, for example, let's look at, if you look at the T, so the x-axis, and we look at the number, for example, 11. Let's imagine, for example, that number 11, we don't know the value of it. Well, as the information is actually encoded into a limited set of numbers, which goes from 0 to 7, it could be easy for me to find where the next value could be. Rather than if it would be discrete, that process will be much more complex to do. So there's a whole field that deals into that, which we won't go into it, which is called error correction. And it's one of the much more important things about the digital world, because it allows us to do computation in top of things which are not perfect. Because if you think your ESP32 sitting here on your desk, sure, the silicon has some problems in it, but thanks that the code and the way we design them takes into account that it needs to correct itself, we could do operations which are correct. Let's say we could do a multiplication and always get the same result, even though what's going inside might even fail. And these ideas are quite complex, and I'm just explaining here so you get them to inspire you. I mean, not to actually tell you that you need to go to the C code and actually implement the things yourself, because these are years and years of research. But again, I think, and one of the beauties of it, of digitation, right, is that instead of having to carry things physically, and instead of having to carry things not just physically, but on a specific domain, we can encode them to symbols and then send whatever you want through them. So if you look at this image here, you could see, you could look at the image in two different ways. The first one is that the Pony Express, which is the man on a horse, is actually carrying the letters physically, and the wires of a telegraph will soon carry things through pulses. But what's more important here for me is that as we are capable, or were capable at this time, of designing a code called Morse code that encode the alphabet into pulses, into symbols, later on, we could invent codes that encode images, that encode sound, that encode wherever we want, and actually send them through pulses and use the same telegraph wires to send them. Of course, telegraph wires needed to be updated because they were designed just to transmit really few amounts of information, not what we are doing now. But still, from a conceptual point of view, you could actually use a telegraph wire to actually send a full YouTube video and it will work. Instead, with the Pony Express, They might need to change the envelopes. They might need to change the number of horses depending on what you send. Because of course it's not the same sending a few letters as actually sending a roll of tape with a video inside than actually sending vinyl with a record inside, etc., etc. So this actually is one of the true beauties of digital. And you see this on your computers, because your computers, even though they are not meant to do a specific thing, they easily can end up doing. Imagine that many of you might have still a DSL connection at home that was designed just for voice. And now, thanks that we digitize it, we could send YouTube video through it, or we could make video conferences. And no one actually thought that this would be possible. And that's the beauty of digitizing, and that's the beauty of your computers, that we could actually send over it. The same that happened to the internet. We could send over the internet videos and voice and many more things. Well, actually, when they design it, they just thought on text, no? And that's the beauty of it. We send symbols instead of sending actually the information itself. And that's the advantage of it. That's led us to a little bit the details of how computers are built. And I don't want to go too much on that, but it's quite a complex thing to get, I think, for all of us, at least if you don't come from that field. It's to imagine that a computer, as the computer I'm using now to talk to you, it's built on top of these simple things called gates, which basically they're just capable of comparing yes or no's, or let's say ones and zeros. And that it's something that it took me and still takes me, I think, for many of us, that we are not people that work on that field every day, some time to get. But it's important that we kind of like take a moment and assume the beauty of it, because the beauty that actually someone, or more than one, but because it's the research of a few people, came to the idea that you could actually use Boolean logic. So just comparing if 1 and 1 are equal or different in a way. I mean, it's a little bit more complex. And then through that, you could build machines that start to do arithmetic operations like adding and multiplying and dividing. And from that, you can start building machines that do much more complex operations, as storing information in complex ways, finding information into information. And from there, build a software as the one we are using now, and build the world's infrastructure. It's quite amazing. And I don't want to say too much.
Before you go on, it's a question. When you say symbols, is it more like a block of binary numbers? I mean, like, I'm trying to like relate how, I mean, like, if you say symbols, the first thing that comes to my mind is an icon. But in computing, I see it more as a block of binary numbers. I don't know if it makes sense, or is it wrong, or?
Thank you very much for your question. It's a really good one, and it's a pity I don't have on a slide for that, and I will definitively add it. So when we talk about symbols, so I think a good way for me to understand this is the following. Ones and zeros, imagine that a 1 is just a yes, and a 0 it's a no. And so the way that we actually store information into the digital world, it's first of all, we need to turn the reality into symbols. So if you look now through your window, you might see it's sunny. And so if you want to actually build a system that's capable of storing the weather, what we'll need to do is first to understand how many weathers we want to store. So we could build a really simple system that's just capable of storing if the weather is sunny or not. So to store that, we'll basically need two symbols. One symbol is it's sunny, and one symbol it's not sunny or it's cloudy. And then actually we could try to see if we could actually solve this question by just using a yes or no question. So is it cloudy? Yes, it is. Is it cloudy? No. So then it means it's sunny, right? Because we decided that we'll just have two states, two symbols to represent. And that means that we could encode in a simple bit, in a simple 1 or 0, the answer, if it's cloudy or not cloudy. Of course, if the question is to store a text, we might need to consider how many letters we have on the alphabet. Let's say on the alphabet, we have around 26 letters, I think more or less, depending on the alphabet, but let's say 26 letters. So we have 26 symbols. And so we might need to think, how many questions do we need to actually answer to define what letter it is. So we could start doing something like, is it a Q or a P? Or it is a, and you might say it is not a Q, but it could be a P, and then you'll compare it with W. Well, I don't want to extend too much on that, but we could do an exercise after if you want to. But the idea here is that a symbol, it's basically let's say the operation, we could say, that we do that when we actually transform our wall, that usually it's continuous and many things happen there and we don't count how many, into something finite. So, for example, to actually describe the alphabet, we'll need to look how many letters, as I say. So we'll say we have 26 letters, so 26 symbols. If we want to transform my voice into a digital domain, we could do it in different ways. We could, for example, consider that my voice is just about frequencies and amplitude. So we could actually try to see how many frequencies do I need to store to actually keep that. Or maybe I could encode it into a different way. Maybe I could encode it through syllables, or by basically just simply encoding the letters I am pronouncing. And the same goes, for example, let's think on a screen on a computer. So a screen on a computer displays color and displays color on a position. So our reality is not composed by specific colors, but it's composed by colors which keep mixing ones with the others. But a computer has a limited set of possibilities, which is around 255 possibilities of red, 205 possibilities of blue, and 205 possibilities of green. And by combining those, it makes all the colors that are visible on a computer screen. And so that means that it's around, I think, 32 million possibilities. And so we could say in a way that our computer screen deals with 32 million symbols or 32 million possibilities. And this way of thinking, you see, from, let's say, mapping the reality into a specific things that are discrete, that are unique in a way, it's what we talk when we talk about symbols. I don't know if this helped clarify a little bit this idea. Definitively, we could cover it more in a separate slide where it's through some pictures, maybe it's easier to understand. So, by the way, please let me know if someone is putting something on the chat. I need to check because I cannot actually open this quickly, just for everyone to know. So let's say we'll stop for a moment, okay, and we'll do a break in about 10 minutes. So don't worry, because I know the things could get a little bit long. I hope everything we said before, it's helping you to understand and to, let's say, go over things that you maybe know already a bit, but that could help you to understand a bit better why we need to learn those things or why we are doing those things. Let's forget for a moment about those, and now we go more into how we actually build those things. So not the theory, but the practice. Let's say something at the beginning when you start to work in electronics that confused me. I remember as a kid opening electronics, I always got confused. It's the difference between integrated circuits and PCBs, and primarily the difference between microcontrollers and microprocessors and integrated circuits. So, well, that's how a circuit of a computer looked on the 1940s. It's built with bulb, which it's something that was there before the transistors. It could even be built with relays. So it was a relays with electromechanical, with bulb was already electronic. And people will basically connecting with wires, the resistors and the bulb. Bulb, you could think they are the equivalent to a transistor together once with the others. And so that's how you will build a system, okay? So if you think that a computer or your laptop now has the order of millions, or in fact billions of transistors, imagine billions of these silver circles that you see on the screen. Imagine like millions of them. Imagine how hard it will be to build them. Imagine how many work hours we'll need to actually solder all these points together. In the 1950s, IBM, I think it was IBM, came with the idea of cards, but actually it was the same idea. The only difference is that instead of putting things connected through wires, they put them on a printed circuit board. They put them on a piece of a material that could hold the components that soldered them. And so that way, of course, they could build computers in a much more standardized fashion, especially because they could say that, look, one of these boards you see on the screen, it's a board, for example, that's capable of multiplying a number. And then if you want your computer to multiply in parallel 3 numbers, you put 3 of these cards. And if you need your computer to actually do another operation like dividing, you might add cards for dividing, and in a kind of more modular way, you could start assembling your computer. But still, as you can see, they are built, these are things which are completely tangible in the sense that you can, with your human hands, you can assemble them and make them. And in fact, that's the way they were built. In the late 60s, something appeared that was quite revolutionary. We found a way about how we actually turn a circuit like this one, which was assembled by humans using solder and putting all the components in place and first making the PCB. We found how we could make all the things into an automated process that basically was based on silicon. And this is how the integrated circuits were born. An integrated circuit, it's basically these kind of boxes that we have around the lab. No, this one is white, but there's in black, and some are so small that they don't even fit. Let's say we cannot even get them maybe with our fingers. We need some tweezers, and some are big, like maybe the one that's on your computer running now, your laptop. But at the end, what we found is that we could actually get silicon and do a photographic process on top of silicon that will change the silicon properties to be a transistor, a capacitor, a resistor. So basically, we found an automated process through light of getting a small piece of silicon and build a board like the one you see here without any direct human intervention. And with a much limited amount of space, let's say, because we could make things much more reduced. And on top of that, we could make things really efficient because they were really compact and done in a way that would allow us actually to put them inside much smaller devices, and so build in a way the world that we live in nowadays. And let's say this revolution in a way got started because of the moon landing on the late 60s, because it was the first time that there was a need to build a computer for the lunar module, the smallest spacecraft that basically brought people from the orbiting module, orbiting the moon, down to the moon. We needed actually for the first time a computer that was really small for the time where computers will sit in an office and occupy the space, let's say, of a floor. Keep in mind that 10 years before this, more or less, so on the late 50s, the IBM CEO said that he thought in the world there was a space for about 5 computers because they were so big and expensive that he thought that that would be the amount of computers that, let's say, the US government and few European governments will buy, and maybe 2 US companies, and that will be all at this time. So we are 10 years after that, and we are already capable of using these things called integrated circuits, like the one you see on the image. Well, not exactly this one, but similar, to actually put them together to build a system which is far more compact than these computers occupying the size of the room. And they said that the lunar program, let's say the program that was put into place to actually build the rockets and the computers and to actually send people to the moon, was the first customer to start buying so many of these new technological integrated circuits. That is the one that actually started the industry, because it bought a lot of components at once. I think it's also a good reflection to see like how actually public money changes the history of humanity in a way, because this was not private money. Actually, we fly to the moon with private money, right? With public money from the government. And this was actually the one who sponsored the digital revolution that we all live in. However, these first integrated circuits, they were not full capable of processing something. They were just parts that you need to process. So let's say one chip will be a multiplier, and one chip could be a divider, and one chip could be an analog to digital converter. But it was in the 70s where we actually decided that we could put together some of these chips and build what we call a microprocessor, or also we could, in a way, for now, use the word microcontroller. And that's really important because it means that we are capable of actually having a full computer in a chip. So a full computer into something which is extremely small and could be made out in an automated manner. So it could be cheap. It could be made cheaply. And this was the Intel 4004. And if you think Intel is still the company that makes the chips running in most of the world's laptops and servers, not for phones, but for laptops and servers, it's still the biggest player on the game. And this happened because I think the thing here is that Intel got in charge. They basically commissioned to Intel to build a calculator, or I think he was supporting a customer to build a calculator, but a calculator that was for business, so should do kind of a lot of complex operations. And so they came out with a chip that could actually run this calculator. That was a calculator that could do like had memory, you know, to store numbers you use commonly and operations and things like that. And that's how they gave birth to that. A few years after, if I give you seats, 71, 76, it happened quite fast. This chip, more than this chip, what followed this chip gave birth to the personal computers revolution. Because the computers on the 70s for big companies, they were still built a little bit that way. So that way here, sorry. Like because they were big and they were designed to last for many years, working always continuously, like in the computer that used to be on a bank on the 70s. But a lot of people like you are, they are starting willing to have their own computers. So they actually went and used these low power, because they were of course not as powerful as the IBM computers, chips, and started to build themselves computers. And so this what gave birth to the personal computer revolution that in a way was led by the Apple I, but there's a lot of that people that actually was before and even was after. So I just choose Apple because I think it's a reference for many of us. And for the ones of you that never saw it, this is how the Apple I looked like. It was like an Arduino board. You'll buy and assemble it yourself and then look for a TV and a keyboard and finally end up having something where you could actually code a small program in BASIC. And just for you to see that personal computers at the beginning were nothing as what we think now about a personal computer, a laptop, or a phone. In the 80s, this got massive, and computers like the Commodore 64 actually started fully this revolution of computers in the houses. And it's important here to keep repeating this happened because someone realized that you could get silicon through a light process, turn it into transistors, capacitors, and resistors, and so on, in a single piece of silicon, in an automated manner, build a circuit with thousands of transistors than before people would have to weld by hand. So in fact, if we think has a lot to do with digital fabrication too, because the process I am describing, I think for many of you, right, sounds more like digital fabrication than analog fabrication. The end is not as different as when you get your 3D printer and you print a part that's flexible in a side because you're using a compliant mechanism that works as a hinge, and then actually your part actually connects with another part, and everything is made out of plastic, and it's just your design that actually it's characterizing the behavior of that element. No? And I think that's something you learn at Fab Academy. So it's interesting to see how all these ideas at the end are connected. And of course, then on the 90s, you got the revolution of the personal computer. I mean, it started before with the Macintosh, but I think many of you got first in contact with a computer, maybe with a Windows 95 or 98. And this was the time of Intel computers with the CPUs, in fact, not that far away from the ones that run your laptops now. However, at the same time, there was another revolution starting, which was the one about mobile phones. So, and mobile phones changed completely the game, because we didn't want computers that were super fast. We were computers that consume as less battery as possible. And this was where the path of low power computers started, which, because at the beginning, no one thought about that. People thought it doesn't matter if it takes the consumption of 2 bulbs instead of 1 bulb. I mean, it's already so few that what I want is speed. But at a point, people realize, no, we don't need just speed. We also need power consumption. We also need to reduce the power consumption. We need low power consumption. And that's what changed a bit the story of computers, because aside from Intel, another company called ARM, A-R-M, started to be on the game, selling chips to many more modern chips. We'll explain this in a moment. But basically, we could say selling the technology to make chips to companies like Motorola, like Nokia, that many of you might remember as maybe the first phones that you got into your hands. Just a comment here, because it's interesting. When we talk about integrated circuits, there's 2 processes, right? Like on Fab Academy. One is designing it and one is making it. So the same that we know that you could make a design for a chair and put it online, and then you could make it yourself on the Fab Lab and sell it, but also someone else could make it in another part of the world, and he could pay you back some money for the design of the chair or not, that depending on the licensing you're using. But these kind of processes are, let's say, feasible. The same happens here. So when we talk about integrated circuits, like for example, the design of the ESP32 that you are using, or the design of an AT-Tiny, or the design of the ARM chip running your Android or iOS phone, one company could actually be designing how it works, could be doing, let's say, the Rhino design of it, the Rhino, the Fusion, the AutoCAD. Of course, they don't use that software, but just for you to get a similar idea. And then a different company with the capabilities of actually putting this into silicon could be building the silicon. And that's actually what's happening with ARM, the company that runs many of the chips nowadays. In fact, in the Fab Academy inventory, there's ARM chips, and Oscar told you about, and there are these kind of chips exist in all your phones. They power all your smart TVs. And ARM, which is a company in the UK, what they actually do is that they just design, they just provide the design. They're like an architecture studio. They just do the plans for it. And then they sell it to people that actually is going to make the silicon. And the way it usually works is that a company, let's say whatever company, from Apple to Plus One. Let's talk about Plus One, like a medium, like Chinese manufacturer of phones. So Plus One might contact ARM and might say, I want this chip. I want to build a chip, and ARM might give to Plus One the different blocks to actually build the chip they want. Like, I want this part of the chip for actually driving the screen, and want this part of the chip for actually driving the main processor, and this part of the chip that are optimized for, let's say, encoding and decoding voice. And this one, which is the Bluetooth, and then they actually will put all the things together and make the blueprint that will send to a manufacturer. That could be a Samsung, because Samsung, apart from phones and TVs, they actually run a silicon factory, let's say, and they will make the chip for them. No, so it's quite an interesting flow. I mean, we could talk hours about this. I'm not an expert, but I think it's interesting that if you want to research on that, because it's interesting as how new paradigms of digital fabrication emerge since the 90s. And well, from that phones to the iPhone 4, which was, I think, for in a way, that the phone that showed to the world that the potential of a touch screen and a good camera for the time into a phone, and the experience you could get from that, and from there till where we are now. And in fact, the chips running on a Raspberry Pi are ARM chips, made by a company called Broadcom. And more than chips, in fact, what they are, it's something which is also adding more confusion today into this world. Because as I said before, when I explained you that Plus One might contact ARM and get a bit of code or of a design for the Bluetooth, and a bit of a design for the CPU, and a bit of a design for the graphic cards, and then put everything together as a design and send it to be made. This is what happens on the Raspberry Pi and this kind of chips. It's what we call a system on a chip. So inside this black square you see in the middle of a Raspberry Pi Zero, actually, there's not just a single processor. There's a bunch of components put together. And that's a little bit where we're going right now. In fact, if you think of the ESP32 you are playing with these days, it's actually a system on a chip, right? It's a bunch of different components, the Wi-Fi module, the Bluetooth module, the memory, the flash drive, and the processor, et cetera, all combined together into a single piece of silicon. So in a way, the line between microcontrollers and microprocessors and CPUs is also blurring away. And this is a Pi Zero that got just 5 years, thanks to this idea of a system on a chip. So in a single automated process, you could add so many features into something. Again, something in here, a couple of things. Well, this is the Fab ISP. It's a board that I don't think you're making right now because things change a little bit, but we don't need to look at that as a board you made. I think it is important to see how actually we get integrated circuits, which will be this black vertical piece of plastic into this board, and actually we populate it around with other components. So if we look with the microscope inside that piece of black plastic on the last image, actually there's also transistors and capacitors. And someone will say, why Guillem, do we need to put an integrated circuit like this one and then populate it around with transistors, sorry, with resistors and capacitors? Why we cannot just put a single piece of plastic with few legs, solder it, and that's all? And the answer is that that's fully possible. That we don't do it because by adding these components around the chip, we customize the chip. But if that you are a big player on the industry and actually you see that you could save some money by making a specific plastic box with the legs, so that actually includes all the electronics in there, and so you'll just have to solder one connector into it, you could go and do it, okay? So this idea, when you look at the PCB, that you see black boxes combined with other components that are more, let's say, maybe we could call them traditional components like capacitors and resistors, and even transistors. We build it that way because it's convenient. No, we basically make into integrated circuits. We make into a small plastic boxes with silicon inside the parts that we need to use a lot, and the parts that we don't need to use that much. Let's say we achieve them, or the functionalities we achieve them by combining it with other parts. And that it's important. I was now using the word plastic in purpose, because when we look at the chip like this, an Omega 328 running the Arduino Uno, but you could look at any chip. When we look at the inside, you always tend to think two things: that this is made out of silicon, and that this is actually a processor or a microcontroller. Just things that it's good to clarify. The outside of this is not silicon, it's plastic, and sometimes it's ceramics, depending on the chip. If the chip is designed to work at high temperatures, it might be on ceramics. If it's designed to work on medium temperatures, it's usually plastic. The silicon is inside it. Okay, you don't get to see the silicon. Usually it's a plastic, it's an epoxy, it's a resin layer. Edu, who's an expert on plastics and composites, much more than I do, could explain you better about this. And the other one is that inside is the silicon, which all these transistors and capacitors and resistors, which is the image you see on the side, with blue and yellow color. But more important than this, it's important to know that these actually, this board, this package, let's say a square with legs around, this plastic square with legs around, is not actually by default a processor. We have some boxes with legs around, which you cannot put code into them because maybe they are simply an amplifier that you could feed an audio signal, and they could, on the other side, you could feed a speaker. Or some of the chips could be an accelerometer that's measuring acceleration. So when you open a circuit board and you see a bunch of black boxes with legs, don't think that all of them are processors. Some could be processors, and some could be other combinations of transistors, resistors, capacitors that you cannot reprogram, that are there to do other functions. So in a way, you could find some which are more general purpose for computers, some are more specific purpose computers, and some are not even computers. They're just doing a simple operation, which we cannot maybe even call a computer because it's simply like an audio amplifier, for example. In fact, to help maybe clarify on this, let me just, so to show you clearly, if I show you, let's say, maybe let me give you a good example. It's taking more than I expected. Let me just do. So if you look inside that board here, if you look inside this board, you might think that black box here is also a microcontroller or a microprocessor, and in fact it is not. That's a board designed to put on top of Raspberry Pi, and this is simply an analog to digital converter with an amplifier. So it's a board that's actually designed to basically transform digital audio into analog audio and to drive in a speaker. So
sorry, Guillem, I don't think we see what you're showing us.
Oh, sorry, you're right. Because I just shared, okay, sorry. Let me just make it here. was nothing really complex, but I just wanted to clarify, and thank you very much for telling me so, that when you look at a board like this, and you, for example, see a black square like this, don't take by granted that this is a microcontroller or a microprocessor. This, as in this case, could be simply a chip that integrates the function of decoding digital audio into analog audio and then amplifying it to drive two speakers that you could connect into here. This is a board for the Raspberry Pi to amplify audio. So actually, that's important because we could start to think that every black box is a microcontroller, and in fact, they are not. So that's what's important to know. Let me just go back. We're almost ready to finish. And so again, hardwares versus microcontrollers. Okay. Let me just, and I will go quick into that. Please interrupt me if you have any questions. But the important thing here is to know that a microcontroller and a computer, they are not two different things. I mean, they are really at the end the same thing because more and more also things are merging. There was a time, it's true, that computers and microcontrollers were two quite different worlds. But nowadays, with this idea of system on a chips, it's hard for me, in fact, to tell you if an ESP32 is a computer or a microcontroller, because you could actually connect a screen into an ESP32 and even install maybe a small operating system, like a reduced version of a Linux system. And at the same time, you could treat it as a microcontroller and not do so. So what I'm telling here is that it's good to distinguish a computer from a microcontroller, but actually the line is getting really, really blurry. And at the end, we'll tend to have what's I said before, a system on a chip that includes functionalities more of a computer, like general purpose computing, let's say the computing power that you need to drive on a standard application like your web browser, and then a specific subunits to do a specific parts like Wi-Fi, like real-time data acquisition of data, like the ones you, for example, need to connect a microphone to your computer, and all these things will be put together into a chip. And so this thing is blurring a little bit, and it's happening so fast that I have to say when we started Fab Academy, this was more clear, but I have to say now, to be fair, these things are getting a little bit blurry. So at the end, we could think about them the same way always. And I think the important point here for you is to think that, as we said before, a general purpose computer, it's something where the code, whatever we make it do, could change time to time. And so we always will have something that we identify as a program, something that we identify as our CPU, as our processor, and something that's our data. And so if you imagine your ESP32 right now, you might have a program that is capable of actually telling the CPU what to do. That could be to actually turn an LED on and off. In the case of how we think about microcontrollers, in fact, the LED will be considered data in a way, because even if it's not storing a word inside your hard drive or an audio file, it's actually storing something temporary at least, which is the status of an LED, which is it's blinking, let's say it's high or it's low, it's on or it's off. And think how in these computers we are using, usually the data is separate from the program. This is called hardware architecture, I think, but we don't need to go into that. But at the beginning, computers were built that way. So each of the red boxes here had a different purpose. One was the one storing the program, one was the one storing the data, and one was telling it what to do. So imagine you are in the 1960s, and what you have here is that you basically are on a bank, and the guy sitting on the on your right has a bunch of cards, that each card contains a registry of one of the employees. And the tape records on the other side include the operations that we'll do in the data. For example, the operations could be basically adding the payroll for each employee, depending on the role and position he has on the company. And then basically the other boxes will read these instructions from the tape and put it into the cards, or the opposite, because the systems could work in a way or another, depending on what you wanted to do. No, but it's clear you have each card represents an employee. You actually check on the tape has a program that tells check the code of the type of role he's doing, and then based on that increase the his wage for that month. No, so you could do these kind of things, and the program is in one side, the data is into the other, and the processing is in the middle. Well, quite boring use of computers if we think in the cool things we do nowadays. That's a computer on the 90s, and still now if you buy a CPU. And again, the parts are separate. We have the processor, which will be this kind of big heat sink on aluminum and copper into the left side. Then we'll have these vertical slots that will be the memory. And then at the end, at the right, we'll have the hard drive. So basically, you will boot the OS from the hard drive. It will go into the processor and through memory and do some things. I don't want to go too much into it because we already talked enough. If anyone has a question later on about a specific computer, we could discuss it after. So the way that actually a computer usually works, I say usually, and that the ESP32 you have or the new 80 tiny chips that you might use have, it's what you see here on the screen in a way. So let's think for a moment. Usually the way this works is that a microcontroller like the ESP32, like an 80 tiny, integrates all the things into the same piece of silicon. You have the program memory, which is the Arduino code, let's say you will put into it. And then we have what's the processor. The processor usually includes three things. One is the I/O, which is meant to deal with interfacing with the real world. Imagine the pins to turn it on and off. Imagine the idea of driving in a screen or driving simply on a small LED, reading a button, reading a capacitive sensor, etc., etc. I know this in a 3D printer, this I/O will be controlling the stepper drivers, and then will be controlling the stepper motors, for example. Then we have control. Control actually. Sorry.
One question. I think that I/O stands for inputs and outputs, isn't it?
Exactly. Yeah. It starts. You say. Sorry. Yeah. Sorry. I took this for granted, and thank you very much for the clarification. It stands for inputs and outputs. Exactly. It's a kind of a short form that in English it's used a lot. So exactly, inputs and outputs. Then control, what we'll do is actually, in a way, I think the easiest way to understand it is to actually control the system. No, it's a little bit like the guy telling things where to go and checking that everyone in the system is happy. It's like the project manager in a way into a project. Then we have the arithmetic unit. The arithmetic unit is the one that will be doing things, for example, as multiplying two numbers or adding a number. And then we have a data memory, which is where we'll store our operations temporarily. So if you think, for example, in a simple code for blinking, we might load the program memory, and we might load the program memory will be there. It's our Arduino code. We load it into our computer, and then will be the control section that will be actually started to read the program. And then it will find that the program actually starts by saying that there's a specific pin that needs to be turned as an output. So we'll talk to the input and output, the I/O unit above, and we'll actually tell, okay, I/O, it's time for you to set pin PB40, or let's say digital 2, as an output. And then the console will go again to program memory and keep reading, and we'll say, okay, now turn this LED D2 into high. And it will do so by talking to the input and output unit and actually executing this command from program memory against the I/O, and it will turn the LED on. And then the second one will say delay for 2000 milliseconds. So the control will actually read this from the program memory, right? Delay 2000 milliseconds. And we'll check with the arithmetic unit to actually keep counting the number of seconds that had passed since it started. This could be on the arithmetic unit, could be on a specific purpose register, but let's consider for the moment that we do this on the arithmetic unit. And the arithmetic unit and the control will work to actually keep track of time for 2 seconds, and then we'll go back to program memory, read the next instruction, which is turn the LED off, like digital write pin number 2 low, and we'll execute this into the I/O. And you will say, what's the role of the data memory? Well, in fact, the role of the data memory, it is that usually the program memory, we won't be reading it every time. We'll move the program memory into the data memory. And we'll use data memory as a way to store temporary values, as for example, how many milliseconds had passed since the last time that we check it, to actually keep counting till 2000. Well, this could look complex or could look simple. And I don't want to stress too much, but just so you see at the end that the things happening inside could be decrypted in a way into boxes and give to each of them a specific purpose and tell them what to do. And also to think that when we code, we are just doing a small part of it, which is the program memory. But then actually all these parts will be solved for us, which is also a way of saying that the computer tries to help us. Because I know that sometimes it looks like the opposite. It's trying to make us things too hard to do. So that's what's going on right inside in a standard Arduino and inside this big piece of plastic there with silicon inside, which is the main microcontroller. There's many microcontrollers. This one, I don't think you'll use it this year, but it's good you know it. It's the Mega 168 or 328. It's been superseded by new processors, but still it's used in a lot of machines that you see around the lab, like 3D printers, etc. And I mean, at the end, once you know the basics, you don't care about what CPU you are. It's just about knowing actually how to look at the datasheet, which we'll do in a moment. So what's important about it is to know that this actually, it's the same as this, in the sense that we just have a piece of silicon and we have to accommodate around some components. So we have a piece of silicon that's a full computer with memory, with an I/O, with a processor, etc. And then we just have to accommodate around some components to make it work. I think you learned about this because you all been building already PCBs. And when you make a PCB, you actually do so. You start from let's say an application node that defines, okay, that's a way you could set it up. And then you come out with your own definition of what you want it to do, what you need to do, what you want to do. And then you actually design it and make it on a breadboard or on a PCB on the milling machine or in another way. Moving forward, it's taking quite long. This thought it would be shorter. Sorry, but we'll finish soon. I wanted to take a break, but I just decided to go over at least for that. So we finish a little bit early in a way, but we'll take a break soon. So I just want to briefly tell you that at the end, everything is about inputs and outputs, as you could see. It's about reading something from the external world, doing some computation and outputting something. I think this is clear for many of you. We already did different experiments. I don't want to go too much into that, but just for us to clarify, let's keep in mind, usually when we talk about computers, we talk about the speed they run, and the speed they run actually, it's not how fast they process. It's about the clock inside the device. I don't want to go too much into that, but I think it's important that you should think that there are some processors that every time the clock ticks, they do one instruction. But there's processors that every time the clock ticks, they do instructions that actually count for more than one instruction, because instructions could be more complex, for example. And that means that the speed is not actually equivalent from one to the other. So you could have a computer running at 700 megahertz. This actually could be sometimes as fast as a computer running twice the speed. And that's because there's some computers that on each cycle, they do an operation that's really simple. And so they need to do a lot of operations to actually beat them. And computers that within a single cycle, they actually could do a lot of operations at once. So imagine an operations could be as simple as add two numbers, but maybe we have a computer that has an instruction that does many things in parallel, like you could add, multiply, and then store a number just in a single cycle. So it means that don't just get confused because the megahertz is quite an abstract thing. But of course, there's orders of magnitude. And we could see that the Apollo computer was even slower than normal Arduino, and that the Raspberry Pi or an iPhone 6, which is already old here, sorry, I need to update that, it's far faster. Then the RAM, it's the memory that we use while we're working. I always said it's good to think of as a desk, and we'll see in a moment what this means. But keep in mind, it's like your desk. And in your desk is where you put things that you are currently working at the moment. And then we have the permanent storage that could be called the ROM, the flash, or the hard drive. And this is a storage where we actually go and pick things, but we don't need to have them on our desk. No, that's exactly what you do when you work. You go and you take things from a box or from a shelf, and then you put them into the desk, you process them, and then you store them back into the desk, or you throw them away, onto a shelf, or you throw them away. Okay, we'll go more into that, but just to refresh so you are familiar with these ideas. In the last row, which is the one I'm talking right now, no, it's just important that you see there says flash or ROM. And just for everyone to know, in case I don't want to create, let's say, I don't want to extend too much on that, but so we all know, flash is a kind of memory and ROM is another one. And ROM stands for read-only memory, which means that computers like the Apollo one, even though they were general purpose computers, because you could change the code if you wanted to, once they decided that the code was ready to be flight, they will store it in a way that you could not modify it. Think in a way as if your computer will have an operative system and a full setup of applications that you won't be able to update. So you'll say, oh, such a pity, because my computer will be the same as when I buy it. But at the same time, think that your computer won't be able to persist data on it. So you won't be able to get a virus, because when you reboot the computer, it will be brand new as if you open it, no? So that's the difference between one system or another. And I think it's just interesting to know they exist. I won't go into that slide because you had a full session with Oscar discussing all the microcontrollers available. And I just want to have a final discussion, moving from the hardware more to the software. So the software. Some of you might be thinking, I guess, what's the firmware and what's the operating system and what's code in general, no? Because, for example, on a Raspberry Pi, we run a Linux stack. On an Arduino, usually, or on any of the microcontrollers, we run a simple software sketch. Well, it's not magic. It's just an abstraction that we came out to make things easier. So in a small computers, because they have less resources, usually we talk about the idea of actually a firmware. So it means like, look, as the computer is quite small, and I want to do something really efficient and on time, I'm just going to write in a specific piece of software to do one single thing. On the other contrary, I want my computer is powerful enough to run many things, and I want to make these things run in parallel. I don't want to be the need to boot my computer again every time I want to change what I am doing. So I will build a middle layer that will be called the operative system that will deal with things like managing the screen, the keyboard, actually of managing that applications could run simultaneously, one near the other. And then the developers, instead of writing all the complexity of the system, will just write the application, which is actually what we want to do. So to show you this on an example or to explain you, think, for example, when someone brought for example, the Zoom application we're using to communicate, he didn't need it to actually write how you deal with the Ethernet, with the Wi-Fi, or whatever other means of communication you are using in your laptop to access the internet. He just called a function called get data from that socket. And actually, the operative system is the one who actually is right now dealing with my network card, either if it is a Wi-Fi card, a Bluetooth card, or an Ethernet card. All this is abstracted. Or the Zoom application is not dealing by printing the pixels on my screen. It's just saying, okay, get these pixels, which is an array, like a grid, like in a spreadsheet, no, and put it there, but it's not actually dealing with all this complexity. Instead, on smaller systems, we cannot put an OS because it will make our system to go too slow and it will add a lot of failures. So we are actually writing the whole stack. So when you are, for example, coding with an ESP32, most of the time, you have to load a library called the Wi-Fi library and set up the Wi-Fi library, and then you'll move and do something. And so you might be using libraries which are like receipts of code, no, that might actually speed up the development procedure, but still you'll have to deal with them. There's not someone telling you things automatically like, oh, sorry, there's no connection right now. No, you have to do so yourself. And the important thing here that sometimes you forget is that there's things that an operating system still struggles a lot to do. So, and that's a misconception that makes many people gets a difficulty to understand why it's the potential of a microcontroller. So there's many things that we do which are extremely time sensitive. Think, for example, on a time of flight sensor, or a LiDAR, which is basically a sensor that's capable of measuring the distance from an object, just measuring the time it takes the light to go back and forth. And that's used on LiDARs, which are used on many robots and automated cars for navigation. Or think, for example, on the webcam now running in my above my my screen, which is actually capturing my image, and it's reading like a lot of light sensors, extremely fast, extremely precise. These things are really hard for an operative system to do. So there it's where actually a microcontroller or a specific purpose computer that actually runs a firmware inside it, it's really clever to do so. It has a small piece of code dedicated to one single thing, and then the OS will talk to that thing and make the full application to run, no? So in fact, we could say that even in a laptop like our laptop, it's full of other small microcontrollers that are not running Mac OS, Linux, or Windows, that are running their own small C code, like your Arduino code, that are the ones actually dealing with these time-sensitive operations, like reading a CD drive, dealing with the Wi-Fi, dealing with the webcam, and then your main computer, your main processor, the Intel processor in your laptop, or the ARM processor in your phone, it's the one that's actually running the OS, that it's capable of doing amazing things, even running multiple applications at the same time, but that it doesn't have the capabilities of actually dealing with such time-sensitive applications as these other peripherals, these other microcontrollers are. So, sorry, go ahead.
I just wanted to ask you, all these microprocessors that are dedicated to different operations in computers, for example, could be, let's say, hacked to change their operation into a different one, or somehow the way they were built from the beginning as one purpose?
You brought a topic which is extremely cool, like really good question, because this is something that, let's say there's full discussions within the hackers community and the security community right now. And this is because, as you said, our computer right now, it has not just a piece of code, which is the operating system running on it. It has a bunch of microcontrollers, which are reprogrammable firmware into them, that are running, and so they could be hacked. And so that's extremely interesting, because we tend to think that the persistence of our computer is just on the hard drive. So this is the idea that if I replace the hard drive of my computer by your hard drive, my computer will be your computer, because all the data, the Windows or the Mac OS or the Linux and all your documents and everything is in there. So I replace it and I got yours. And I even take out my hard drive and no one knows what was inside that computer anymore. But this is not actually true, as you said, because we have all these small microcontrollers that before they used to be designed around read-only memories. So a memory that was put on factory time and nothing changed. But nowadays, to make them, let's say, more customizable and upgradable, most of them, they run software that could be updated from the main OS. So the main OS could actually flash the same that you use Arduino to flash your Arduino. Your operating system could reflash some of these microcontrollers to change the behavior, to improve, to patch vulnerabilities, etc. But at the same time it does so, it means that someone could hack into your operating system and actually change the firmware of the code running your webcam. And for example, there was a case, as many, that they achieved to turn on off the webcam without turning on off the LED near the webcam. And so they basically they basically succeeded to hack into a computer's laptop and change and reflash the microcontroller running the webcam, and basically remove the line that was saying digital high, you know, like digital right high, the LED, when the webcam is started. And so they were able to record people without them noticing. So yeah, that's a really interesting topic happening nowadays. And there's a lot of discussion and there's a lot of things being done right now. And in phones, for example, where these things are getting more and more, let's say, complex, you have to imagine now we're at the point where there's encryption in the software running inside all these different peripherals, and the OS is capable of actually validating if the firmware is actually, let's say, the firmware that it needs to be or not by checking the code against specific keys. So it's quite a hot topic. It's really interesting, and we'll see where it leads. But the truth, as always, is that when we get complexity, it's easier than we get hacked in a way. So compiling and programming languages and tool chains. So, well, programming languages, no? we, as humans, once we had the amazing idea of the general purpose computer, we had to actually start designing a way to code for it. And so we need to come up with languages like the English language we are using right now that were convenient in the sense that were enough easier for us to speak, but still enough, let's say, complex to express all the feelings that I want to communicate to you. And so here comes the field of computing languages. So just to say clearly and quickly, if we think, for example, on the standard Intel assembler, which is the let's say the most basic language.
Sorry,
you could.
Can we have a break?
Yeah, sure. I was. Let's have a break. I'm really happy to do so. Yeah, maybe the class will extend for 15 minutes more. So instead of at 12:30, we'll finish at 12:45 because we are a little bit slower than I expected. But if everyone's happy, let's go for it.
Okay.
Gracias, Guillem. Thank you.
A vosotros.
Merci, tío. Top.
Recording resumed.
Okay. So should I go ahead, Oscar?
Yeah, we gave more than enough time.
Okay, perfect. I'll go ahead. So I close this. Is my screen fine? Yeah?
Yeah.
Perfect. Super. So just recap, we talk a lot about what is a computer, why we build computers, what's an integrated circuit, how we lay down on PCBs, what is a microcontroller, and what's an integrated circuit, and that's another thing than just a microcontroller. And so narrowing down that path towards how we actually use them, we are near by the final part of it, which is how we actually code for them. And as I say, coding, it's not something fancy that we invented just because we wanted to, let's say, be cool. It's just we tried in a way to come out with a way that was meaningful to express ideas about what computers should do. Of course, languages or computing languages or programming languages have been designed not always to be the easiest ones to understand. Some ones we primer expression, which means making machines to do really complex things. Sometimes we want them to be easier too, but sometimes also we want them to be efficient, so to be designed so they actually run really fast on the computer, even though it takes years for the developer to study how to code them. So we cannot take for granted programming languages are easy, but they are there to be convenient. So they are there to be useful. They are there to help us do things. Let's say a computer, a processor, it's designed around what is called an instruction set, which is basically an amount of functions that are built inside this computer. However, these instructions are not cool functions like the ones that we will expect, like, for example, take a picture or send an email. These are much more low-level functions. And these low-level functions include things, for example, as moving information up and down or adding to numbers. So if we look how a standard Intel 86 architecture, which is really a standard processor phone, in fact, your computer could even be considered in a way this architecture, even though it's a little more modern, would do on its core, an operation like the one you see here about adding two simple numbers will be by combining these three instructions and doing 4 steps. So basically, it will use the instruction to actually allocate number 1 into a registry, which will be like getting number 1 and putting it inside a box on the computer that will refer from now on as R0. Then, of course, we'll do this for the second number. So store the second number into box R1. Then it will look at these 2 boxes, box R0 and box R1, and we'll add them together by using the function add, and we'll store the result into R5. And then finally, it will move what's on box R5 into the variable sum. And that way, it's how a computer will actually do a sum. So you see there's a lot of moving of information up down, but at the same time, on each movement, there's a few information that's processed. No, so we could say, as we went at the beginning of the class, as we started with this idea that we try to favor operations which are complex because we do a lot of them, but at the same time they are simple because they're just like really simple manipulations are done on the information at every time. And by adding a lot of them together or even in parallel, then we succeed to do things that look complex into our eyes and look even difficult, I would say, into our eyes by just adding a lot of simple steps together. So that's how you will write the code actually with assembly language. Assembly language, I have to say, it's less and less and less used every day more because it's really domain specific. So it has the issue that when you want to move from one processor to another one, you have actually to change it. Because one computer would be using the instruction LDR, and then your mobile phone instead of LDR might have a different instruction, and so you have to change them from platform to platform. So you have a really good library for, let's say, dealing with graphics in your computer, and then you move it to the phone and you have to write it fully, and that's not that much convenient. But if you think who's still using this kind of language, well, I don't know it's nowadays, but at least all the games that you play as kids on your Game Boys and Nintendo 64s were fully coded that way, because that was the only way they could make computers that were quite cheap as a PlayStation or Nintendo 64 do such amazing graphics as they used to do, because the code was really optimized and they wouldn't care if they had to invest a lot of man hours to do so. But nowadays, this is not used that much. It's just good to know it because that's what's going on inside. And that we don't use assembler doesn't mean that people coding in much more advanced languages as C, for example, as you are using to code your systems, doesn't know about this. Because people is actually coding in C, but knowing what's under the hood, and so optimizing the C code to actually generate as much neat and fast and efficient instructions. And you might say, why do we need to do so? Well, imagine an instruction that your computer does a lot of times. Like, for example, the instruction that actually changes the color of a pixel. So if you calculate the amount of pixels on your screen, you might see it's quite actually a big number. If you multiply, let's say, full HD display, will have easily, could have easily a few million pixels, let's say 2 million pixels, and each one has 3 colors like red, green, and blue. So, and it refreshes maybe 60 times per second or 25 times per second. So if you actually improve that instruction that it's done so often, you could actually take, you can speed a lot a program just by implementing, by optimizing a specific function, no? And that's why people spend time on these kind of things, not because they like optimization, because actually they make sense, no? So actually, when we talk about programming a chip or dealing with a microcontroller, we always talk about the things. Now we talk about the hardware, but also we talk about the software. And in fact, when people say the word Arduino, many times they think that an Arduino actually it's this board here, let's say, or to have it more clear, people think it's this. This is an Arduino. Well, this is an Arduino Uno, but actually, for us in the Fab Lab, when we use the word Arduino, we usually refer to that. We usually refer to a specific chip that's compatible with the Arduino platform. And so we could use the Arduino software or another platform that uses the Arduino libraries, like Platform IO, to actually code for that chip. And so this goes because someone actually took the time to create neat libraries that implement the Arduino functions like pin mode, like digital bright, into the actual instructions the chip needs to operate. And then they will be basically going into getting these things to work. So you might think, well, still, I think, after what I said, it can be complex to understand actually what's the difference between Arduino and C++, what actually means to compile code, and how actually we go from compiling code to putting it inside our microcontroller. So let me show you this. I mean, I don't want to go too much on that, but the first important thing to know here is that all the microcontrollers you'll be using, you'll be programming them with C or C++. The C language was invented in the 70s. At the time, it was a super high level and modern language. Of course, nowadays, it's not modern anymore. and it's not a high-level language, as there's language which are higher, as Python. We use the word higher, the more abstract they are from the hardware, but still C is a primary language nowadays where the wall is built upon. Because even though we might use much more abstract languages to code things like Twitter or Facebook, or when it goes actually into the code that runs into the servers that then are capable of executing this other code on top, is actually everything C. The Linux kernel, the Linux operative system, your Windows operative system, your Mac OS operative system, even some of the core applications of it might be written in C. Of course, then on top of these, you could actually run codes like Python and Java, which are, let's say, I wouldn't know if the word is easier, but at least they are designed to do things which are a little bit more abstract. You know, abstract means basically you care less about the hardware and you care more about what you want to do in an abstract way, in a world where we don't have actually LEDs and buttons and processors, where we just have data as an abstract idea. So at the end, we could say that nowadays the wall is still, when we need to deal with hardware, as writing something on a flash drive, as dealing with a USB communication, as dealing with a Wi-Fi card, we use C, the same that you use in your microcontrollers. However, when we build applications on top of those machines, like for example, the code that runs the Google search, or the code that runs the Twitter or Facebook, or the code that runs an application like the Keynote, sometimes we choose different languages than C because it's more convenient. But so the two languages, or let's say C at the end, is living nearby many other languages nowadays. And still it's there. And it's not that you are learning it because we want hard stuff and we want to teach you old school stuff. We actually show C because it's still at a standard. It's still the way that you manage hardware. This doesn't mean, however, that there's a whole new trend about how you actually start to make hardware more accessible by using languages that before were more designed to just deal with data, as for example, Python, and you bring them close to microcontrollers. And you might maybe know about MicroPython, for example, which is a project about using Python to code on microcontrollers. However, again, when we want to do things which are time sensitive, which needs to be really relevant, we always go back to C. So, and time sensitive, don't think that you need to be time sensitive to be at NASA. Don't think that time sensitive is about rockets. Actually, if you think on any 3D printer at the 3D printing lab, in the Fab Lab, that's actually moving 3 or 4 motors simultaneously to draw a circle, just a delay in one of the motors would mean that we don't have a circle, we have an ellipse. And so that's why we need precision. So just a short reflection, because we can easily think that precision is just something for rockets, and actually we need it just to make circles with a 3D printer. So going back here, okay, we are on C code, okay, and so let's see how C code is built and how we use it ourselves. If you use C code, but you code in an Arduino environment, your file is not going to be called C. It's going to be called INO, like blink.ino, from Arduino, of course. And so what happens when you actually get that file that says void setup, set digital pin mode, let's say 2 as an output, and then you go to void loop and you'll say digital write, this pin high, and do something, and then the other. What's going on there actually? Well, this code actually is almost C++ code, with a few differences, which makes it different than a standard C code file, because it includes pre-built functions like, for example, the setup and the loop, etc. And it can understand easily what a digital write is, etc. And this happened just because when we compile the code, to transform this into a C++ code, we add a header file, we add a library that's called the Arduino.h. So the same, if you ever use Arduino and you load a library to actually do something like driving some LEDs, or a library for managing a servo motor, or a library for reading a specific temperature sensor, you load a library on top of your code that was called maybe Wire, or was called NeoPixel, or was called SD. The same, under the hood, the Arduino IDE or Platform IO or whatever compile chain you are using, it's loading this Arduino header inside your Blink file. And this, it's important because it means that once the Arduino header is inside your blink.ino file and your file is renamed blink.cpp, even though actually it changed almost nothing, just having all this Arduino information, all this Arduino library inside, all this pre-made code, it allows the code to be ready to compile. And compile basically means that it's actually transforming all these instructions that you type in the C language or on the Arduino language into something that looks a little bit more like what you see here on your right. It means that it's transforming them into instructions that your processor could execute. And so basically, in a way, it's transforming your language, the C language in this case that was meant, or the Arduino language that was meant to be expressive, easy to remember, and typable on a standard keyboard, into a language which is optimized for a machine to execute. And to do so, we use something called a compiler. And the compiler, basically, it's this piece of code that actually is capable of transforming one language into another, or in a way transforming a language into instructions that a machine could actually run. There's a compiler, it's a software also. So it's interesting, no? Because it's like a rubber machine. Like a rubber machine is a 3D printer built out of plastic parts that you print with the same machine. So it's cool to think, no, that actually a compiler is a piece of a code written within the same language many times, but that's able to generate more code with it. So the standard compiler we use here, it's called a GCC. And just quick note on the quite quick side note. GCC is a compiler which is open source. That means that to turn an Ino file or a C++ file actually into machine code, we don't have to pay money to anyone. It's free for everyone to use. It's free for everyone to turn C code into code that goes inside a processor, in this case, an Arduino compatible board, but could also be your Intel processor in your laptop or the ARM processor in your phone and running. This wasn't like that before. So at the beginning of C and all this world, if you are back on the 1980s, people used to pay for that software, the same you pay for Photoshop or you pay for a Microsoft Word. And so there was a project started called the New Project on having an open compiler that anyone could use to create C code. And this was the father of the Linux project, because of course, if you want to write an operating system which is fully free on Linux, fully free, like Linux is, you actually need first a compiler to code it, no? In a way, it's like to say, if you want to build a free Fab Lab, which everyone is free to access and change, you actually need to build free machines for it, no? Machines which are open source. So think how one thing led to the other. So thanks to that people and to a huge community of contributors, some from private companies, some individuals, we have this tool called the GCC, which is a software like Microsoft Word, like Photoshop. The only thing is that usually it doesn't come with an interface with graphic buttons. It comes as a utility that usually we use on a shell, but we could put in front of it an interface like the Arduino IDE does. The Arduino IDE basically creates a beautiful, let's say, graphical environment where to trigger these tools that you see here on your left. So the ABR GCC, it's a piece of code that actually goes, or the GCC, because in your boards, maybe sometimes it's not the ABR, it's another, let's say, another particular type of compiler of GCC, another, let's say, family of GCC compilers, we could say. It actually goes and takes this file, which is the Blink CPP, the text file, and turns it into what we call an object file. Well, we don't need to go that much into what an object file is or not, but basically think that you actually get your code and you actually compile it into something which is machine code. So your processor can understand it. And so this ABR GCC box here in purple needs to be aware of what kind of architecture, what kind of processor we are targeting. And will actually, that's why when you compile, you need to select, I want this for an ESP32, I want this for a Node MCU, I want this for a Mega 168, because depending on the chip, this process and the instructions it understands, it will be different. So again, it would mean that these instructions here called LDR or ADD or STR might be different from chip to chip. Some chip may even have an instruction that gets all these 4 instructions into a single instruction. So the compiler takes care of abstracting the things for you. And in C or in C++ or in Arduino, we'll always be writing what's here in the left side. And that's the beauty of it at the end. After that, basically, if you're using another library, like imagine you are dealing with NeoPixel lights, which are these super cool LEDs, you could change the colors. It might be adding in there another library, like the NeoPixel library in this case, and maybe this library even depends on other libraries, like the SPI library or any other library that this uses. And it will compile them all as object files. And then finally, it will generate this NEL file, which is basically, it will consolidate or join together all these different object files of pre-compiled code into a single file. We don't need to go that much on that, but people might say, why so much complexity, like C++ object files, why not directly a next file or a binary file I could put into my microprocessor? Well, this usually is done because that way you don't have to recompile parts of the code that you are not changing. And so you might notice that sometimes when you compile the first time a code, it takes longer than the times after, because some parts of the code, they don't need to be compiled if you just change a bit. So that is why we compile things separately as Lego bricks, and then we assemble together into an L file. And then we generate an X file. Usually, it just return these into an hexadecimal standard, nothing to worry. And then finally, we create a binary file that it's actually could be an X file, depending on the, let's say, the way we are loading the information into our computer could be in a way or another. And here it's important to understand, actually, if this process we will be doing it not to compile an application for our Arduino or microcontroller, but to compile an application for our PC or laptop. Then in here, well, we'll do the same procedure exactly. The only thing is that this file that's called .x finally will be called a .bin or a .exe in Windows, an exe file that you all might be familiar with, and then you will click and it will open because Windows might know how to operate and run it. Of course, you won't compile it using the Arduino.h library. You might compile it with a library that's designed to run things on your computer. In maybe would be the, let's say in Windows, the System32 library, and maybe even the Net library, which are libraries on Windows for building applications, or in macOS will be the Cocoa library that actually allows you to build macOS applications, right? But at the end, is everything the same? We are not teaching you something, we're not discussing here about something which is just for microcontroller, just for Arduino. Once you know these concepts, they are for any language. Even if it's not C, even if you are talking about Java or Python, even if you are talking about languages which are really different, all this process is happening always in a way or another. When we have the binary file, we start something that is another question, which is, okay, I have a binary file in my laptop, but now I have here on my desk a microcontroller, I have a board, I have an ESP32. How do I put this piece of file, this intangible thing in my desktop inside that thing? And that's the next step, no? That's how we flash, how we actually get this code and we put it inside. And you might think that that's something particular from microcontrollers, but actually it is not. It is not, because this is actually what happens into your computer too. So think your computer. Your computer has a microcontrollers, as we said before, managing your webcam, your keyboard, and has a main Intel processor sitting there in the middle, and maybe even an NVIDIA graphic card. Well, suddenly, we need to get and actually boot the system. So we have a hard drive, which contains maybe Windows or macOS or Linux, and we want to start it. We maybe even have two OSs. Maybe we have Windows and we have Linux, and we have to combine them. Anyone trying to talk? Okay, no, sorry, because I listened to some noise. I thought maybe someone wanted to say something. So your laptop actually has what we call a bootloader. It's a way inside your processor to actually turn on the processor, check the hard drive, and even if you have more than one operating system, present you on a screen where you could actually choose what OS to load. If you ever play with installing maybe Windows on a Mac, you saw something similar, or installing Linux into a Windows machine, you might saw both of them. So the idea of a bootloader, of a piece of software that help us load code, it's something that is a standard all over systems. The kind of bootloaders we'll talk about it today, they usually are small pieces of code that live inside our Arduino. And by Arduino here, let's think an ESP32, a Node MCU, an Arduino Uno, let's say that sit on our microcontroller and that allow us to put a code into our microcontroller in a convenient way. So when a device doesn't have a bootloader inside, what usually happens is that we need something called a programmer. A programmer usually is in a specific dedicated piece of hardware, like the ones that you build, to actually get code from your laptop and then put it inside one of these microcontrollers. So the idea, in a way, it is microcontrollers by default, they don't speak protocols, which our laptops do. Our laptops, sadly, they just speak really few things nowadays. They speak USB, USB-C, right? Because it's even getting harder to get a standard USB. And they actually use, let's say, might have a Wi-Fi connectivity, not even Ethernet connectivity nowadays. So how we actually get information from our laptop and we put it inside such a small microcontroller? Well, to do so, actually, we could do two things. As I said, you could build a programmer, you could build a specific kind of hardware that talks, for example, USB, and it's capable of flashing that microcontroller. But that means that you'll need to carry always this small piece of hardware with you when you actually want to flash a microcontroller. So what we usually tend to do is to put a piece of software inside our microcontroller, inside the ESP32, that allows the ESP32 to be programmed in a much more convenient way. And this is what the ESP32 you have does. It has usually a built-in serial to USB bridge, either an FTDI cable outside or a built-in integrated circuit into the PCB. So you are giving the possibility to the ESP32 to be programmed not just through a specific programmer, but through USB, which is a standard interface in our laptops. If our laptops will talk serial like they used to do in the 1990s, we won't be using this. We might connect the ESP directly to our computers using a standard serial connector, but nowadays we need those. And on top of that, we'll put in a specific piece of software inside the ESP32, we'll call the bootloader. So it can recognize code sent through USB and load that code and run it continuously. So the bootloader, in a way, is like a simple piece of code running inside our microcontroller that allow us to load code in a convenient way. Bootloaders are all around, and as I said, even your computer in a way has a bootloader that allows to get information from the hard drive and start the operating system, and even allowing you to choose what operating system to boot. So at the end, it's nothing, let's say, fancy, it's nothing weird, it's just a convenient software that we design and build and put inside. And for that, you might see it's quite common actually on your boards to actually start in a way where you first of all put the bootloader inside your microcontroller using in an Arduino Uno, for example, what we call the in-circuit serial programmer, which is this 6-pin connector that you see here on the right. And once the bootloader is inside the chip, then the chip might know how to get code from now on through USB. And of course, if one day we want to change the bootloader, we can go and reprogram a new bootloader through the in-circuit serial programmer, or even decide that we don't want to use the USB anymore for programming and just keep loading our codes through the in-circuit serial programmer. Of course, with the issue that we'll need always a hardware programmer that can turn USB to this 6-pin connector every time with us, which could be a little bit annoying to do so. And just for you to kind of finalize this chapter on bootloaders, I think nowadays a really common type of bootloaders are what it's called OTA, over-the-air bootloaders. And that's a bootloader that you might find inside home appliances that connect to the internet, like an Alexa device, a Sonos a speaker, or maybe your ESP32 even, which allows a processor to download a file from the internet, which is a new piece of code, download it, reboot itself, and then start from booting from the new piece of code it just download. So in a way, do a full software update. No? So as you see, bootloaders, they have a long living. They're not something from the past. So this will be the main introduction to bootloaders and flashing. You see at the end, what we are doing is that inside our microcontrollers, we have a memory that stores ones and zeros. and that we could imagine them as switches that could be yes or not, on or off. And then basically we create a code with C or any other programming language that we compile, and once it's in our computer describing how the switches need to be turned on or off, we need a way to actually get those and move the switches inside our microcontroller. As our microcontrollers, they don't have a switch panel where we could switch on and off and do all the combinations, and also be super slow to do so. What we have there is basically a way to actually get this file describing the switches which are on and off, and actually getting those flash inside our microcontroller. So a convenient way of transferring these instructions from our computer to our microcontroller through a bootloader. So that will be the end of the game in a way, because that's the way that we'll program all sort of microcontrollers and processors. I don't know if this has been helpful. If there's more questions, I know we don't have that much time because the Zoom link is actually booked for another class. What do you think about this? Is it helpful to start understanding a little bit these things? Yeah?
Yes, for me.
So before we finish, I keep saying before we finish, I'm sorry, it's a little long, a lot of content. Let me just show you a little bit how we actually learn how to manage a chip. Because you might tell me, look at them. You tell me this is super fancy, these are the instructions here, we could even go, and you are telling me these are the pins. But now let's think that we don't have Arduino, that Massimo Vanzi and his friends, they never built that board. We are just looking into DigiKey or to the microchip website, looking for the next microcontroller, the next processor for a project. And so, okay, and we found it. We found a processor that's perfect. It can, you know, we are building an MP3 player. Well, that's a bit old school. Let's say we are building a camera recognition software for our bike to basically tell us where the street lights are in red and brake automatically. So, okay, I found that amazing processor. It has like the speed I want. It can run like machine learning operations inside to learn from the image it's doing. It can drive a camera. Amazing. Okay, but how I actually go and start knowing what to do with that chip, what's possible, etc. So data sheets, right? And data sheets is something that you actually might know already. But we did an exercise, as you might remember, at the MDF in the Unpacking Intelligent Machines exercise on that. And I just want to show you briefly on that. No, so if you look at the data sheet, at the end, it's a convenience. Let's say it's a convenient way of that the industry took to actually organize information around the products they sell. You know, it's like on IKEA, you have a brochure explaining each piece of furniture. The electronics industry does the same. So let's look at a simple data sheet. Let's look at an LED data sheet. This is another Fluid article that explains you how to read a data sheet.
We cannot see it. We're looking at your screen.
Sorry, I always forget about it. Thank you very much. Do you now?
Yes.
Thank you. So, as I said before we quickly look at the datasheet from another microcontroller that you'll work more closely with Oscar in understanding how to do so. But I just wanted to introduce it so you see that everything we said today, it makes sense in a way into what you'll do tomorrow. So if you go and you check on an LED datasheet, as the one I have here in front of my screen, well, in fact, this is an article from Motherfruit explaining how to look on a datasheet. So really, really convenient or interesting to read through. This is a datasheet from an LED. That's a simple, basic 5mm LED. And so you always start on a datasheet and it has a list of the features it has, right? Like there's a low power consumption LED. It comes in a specific package, which means the physical size of it. It has general purpose leads, so the path, let's say that the connectors of it are standard. It's reliable, it's rugged, it's long life. Well, at the end, it's like advertising what it is. And then we have a description, okay, with super bright red source color device made with gallium aluminum iron side red light emitting diode. You'll see these people, they use a lot of technical vocabulary. I mean, we are here into the wall of true engineering in a way, right? I mean, imagine choosing an LED for your board, it's something quick, but choosing an LED that will go into a product that you'll make 1 million of them, you might maybe take some time deciding what LED you put into it. But if you look at, usually the thing we go straight into are two things. The first is the electrical characteristics, which basically we want to know, okay, what's the voltage to drive this? Well, it says here that the forward voltage of this LED, let me make this bigger, it's 1.86 volts, and that the maximum one is 2.5. So if I put 2.5 volts in here for a long time, I might burn it. The standard voltage should be 1.85. Okay, and so you see, give a lot of data that you might say, Guillem, how do I actually look at that? But that if you look at, if you are, let's say, designing a circuit and you are following a tutorial, it might easily tell you, okay, go to datasheet and look for that particular value. Or if, for example, you are coding a system where you put LEDs, they might tell you, okay, go and check the forward voltage to actually know the resistor you need to put in series with your LED. So in a way, it's a long process to actually go here and know what everything means, but you don't need to do so. The same, you have the characteristics. You might have absolute ratings too, in maximums and minimums. You might have some charts explaining some parameters that could change over time, over temperature. And finally, you will have usually two things. One, it's, well, in this case, it's above. It's a package, which is actually what size it has, so you know how to actually design a keycat or an eagle way to fit it there. And the last one is actually how it's packaged, because again, if you are designing one board, you don't care. But imagine you are an engineer putting a plan to assemble 1 million TVs. You actually need to know in what kind of boxes you'll receive the thousands components inside a TV to actually try to see how you'll deal with the stock and with the machines, etc. So that data sheet at the end contains information that many different people might look at it. Engineers, developers on the software of the machine, but also logistic guys, etc. Now let's go into not something as an LED. Sorry.
I just sent in the chat the link of the FabLab inventory.
Oh.
That if you click on it, you can go and see the serial number. So
Exactly. Let's do so. Thank you, Edu. Chat.
No,
so
sorry, it's not this one. Oh, I made a mistake. This is all the FabLabs inventory. We have
okay, you want the FabLab Barcelona inventory, right?
The FabLab Barcelona inventory is this one.
Amazing. So, that's really cool because you know, like this year the team is doing a great effort for the inventory to be available and properly stocked for everyone. You even see that the Raspberry Pi now updates the values, which is super cool. So. If you look at any component here, even if it doesn't have the datasheet directly linked into it, if you get the reference of it and search it, we could do so. So it says here, there is a LED red clear LED into a 1206 package. So in fact, if I go here and I copy this and I put this datasheet, you might find.
You don't need to even put datasheet. It goes directly to the DGT link.
You're right. Let's do those. Yeah, so we have it here on DigiKey. And now I could actually go and I could go to the data sheet and you see it's actually here. Boom, 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 loading. And data sheet, again, and you see, now that I did the example before, see how it replicates. We talk about the features, package dimensions, so we know. So keep in mind, like, I mean, for sure you already checked that in one of the classes, but each of the blueprints you use on KiCad or Eagle to set a component, someone took time to get it from here and design it there on the components library. And then all these values and characteristics. Well, as a way to finish, what I wanted to show you is how actually the datasheet, and I will paste it now on the chat. Sorry. So this datasheet, which is for one of the microcontrollers that you could use into the Fab Academy this year, which is the ATtiny 1614. So that's the datasheet, the same as for the LED. Nothing, let's say, new. but of course from a computer, not from a light. So the same that the brochure in a light you buy in IKEA, it's 2 pages, and the brochure for a new laptop might be a few more pages. The same happens here. So there's much more to be told about this. And in the introduction, what you have here, it's, yeah, exactly. Yeah, 623 pages. So what I'm saying to you here is that you don't need to go and read the 623 pages, but you need to know at least that the people who wrote the libraries you'll be using, so when you type a digital read or digital write, the code executes the right instructions for this chip to do whatever you want it to do. Read those, at least a part of it. At least check that the documentation on the ATtiny 1614 is maybe the same as the ATtiny 44, which was a chip that already existed. So in a way, he checked if the code that the Arduino community built 10 years ago for the ATtiny 44, it's compatible with the ATtiny 1614. So you've seen a way the way people work with that, no? And so characteristics about the computer, and you talk about the CPU before, you remember, we talk about the memory, we talk about the system, yeah, I mean, we talk a little bit about operating systems. This is a bit more complex than this, but what you'll see here, if you start scrolling down, it's actually that it goes and it covers all the different parts that the processor is built of. So in a way, what we are doing here, it's putting names into this, right? So we look at this black box in the right, and in the left, there's an X-ray, let's say, of the chip with everything that happens inside, with the millions of transistors that are built inside the chip. So in a way, the data sheet, what's given to us, it's in a way telling us what this small image with such a complexity that we cannot even understand does. And it does this by covering all the parts on the chip. There's a lot we could talk about this, but we're getting short on time. But what I think in the class tomorrow you'll cover with Oscar is actually how all these parts are actually set to work together. As a way, I think what I will recommend for today, I mean, and Edu and Oscar will tell you more, but what I will suggest is a way I do look at the data sheet. It's first of all, I will start by looking at briefly into the chip, the way it's built. And not because I know all these parts, but because here it will tell me a little bit what's in there. So it will tell me inputs and outputs, and in fact, each of the sections on the data sheet will be linked to one of these sections. This is quite complex stuff. So in the class tomorrow, you'll see more. And also keep in mind that we have the documentation already ready on the embedded programming, where we are actually mapping how all these things work. So I don't want to extend too much because I'm sorry, I think this Zoom link is booked. Could you confirm, Santi and Oscar, this is?
Well, I think the meeting extends only till 1, but it's fine. I think we can extend it if need be. I mean, it's not going to come from 10 seconds.
Okay. So if you want, I'm just going to give a quick overview on that document. So tomorrow on the class, people actually can check this before a little bit. Do you think that's a good way?
Yeah, it's fine.
Perfect. I'll do this briefly. Tomorrow you have a session with Oscar where you'll cover more of this, but I just want to give you a short introduction so you don't think that we are, let's say, just trying you to tell you to do something that it's impossible in a way. Because I know sometimes in Fab Academy you could easily feel like that, like why these people it's making me do things. It will take me ages to do so. The documentation on that page is based on the ATtiny 44. It's really similar to the ATtiny 16, the ATtiny, sorry, I have here 1614. We haven't yet updated that page because, as you know, there's been some changes, but it's almost the same. And what I want to show you here briefly is that usually we live in this world of Arduino where things are made easy for us. So the Arduino abstraction basically tells us that to blink pin 6 on this and put an LED into it, we just have to write this code here, right? Digital write, high-low. I think more or less many of you start to be familiar with this. However, when actually we run this, we need much more things to happen. I mean, that is where the datasheet is explaining this, because actually if I go to the instructions, in here. Wait a second, I'll keep this for later. So when we go into looking what actually is going on inside the device, it's much complex than just these sentences that you are seeing here with the digital bright, high and low, etc. What we are actually doing here is that we are actually moving a lot of things inside the processor, and the datasheet could tell us about this. First datasheet will tell you how the memory is organized. And you remember before we talked about the program memory and the data memory? So actually, if we go, if you go here and you type data memory, and I click here, you see? That's explaining to us how the data memory is structured inside. And this basically tells us that in here, that from all the flash, which is this is all the memory available, it's divided into 3 parts in this chip. One is the boot code, where the bootloader is stored. Where is the application code, where your code on Arduino will be put and will be executed. And the other one is the application data, which means all the data that will be moving in and out. So for example, if you actually are counting the number of times a button is pressed, this counter is stored on the application data. For them to take a decision, like for example, when it's pressed 15 times, go and do this action. So the memory, as you can see, it's divided into these different parts. And there's a specific part of it that it's the one that's the most interesting to look at such a data sheet. It's called the registers. The registers, it's quite a weird thing because I think we maybe talk a lot about many things, but we haven't yet introduced the registers. The registers is a specific kind of memory that when we write things on it, actually it does things. So let's think that the memory in our computer, in our microcontroller, is like a bunch of boxes. We have a lot of cardboard boxes labeled with names, so we could identify them quickly. And so there's some registers, which are usually these registers at the beginning, these 32 registers, that what they do is that actually, when we put something into them, they might actually do an operation with it. Let me show you an example of these registers, because it might look a little bit complex and it's far easier than what it looks like. So when I said here that actually we applied this add instruction, right? What we are doing here is that we are putting these numbers into a register that what it does for us is to actually add them together. So imagine that we have a box that when we actually put 2 things inside it, 2 numbers, it adds them together and we can then go and get the result from it. So registers could do kind of magic things like that. And then there is another set of registers, which is the one that actually it's much more interesting for you to know, and the one that on the data sheet you might need to go and check, are called the I/O registers, or the input and output registers. And those registers are the ones that when we put something into them, so imagine you have a box, it's a box that when we put inside a 1 or a 0, what they actually do is that physically outside the device, they actually turn a pin on or off. They are the ones actually that when we do something like digital bright high or digital bright low, we are interfacing with them. So in a way, every time you do a blink on an LED, what you are doing is you are writing 1s and 0s to a piece of the memory or the data memory called the registers. So in a way, what you are doing is that you are running a code on the program memory that's telling the data memory and a specific part of it called the input and output registers to actually put a 1 or a 0 into a specific register that actually affects a specific physical pin on the device. And this pin is actually controlling an LED that's blinking. And so that's the full understanding of the blink, let's say, goes to that direction. I won't want to extend too much on that because we'll go too much into the core of actually how you deal with registers. But it's important that you start looking at the datasheet for tomorrow, looking at that if you go and we open this datasheet, for example, and I go to register summary, and I start here. Let me show you. And you start scrolling through registers, non-volatile memory controller. The chip starts to be complex, and datasheets start to be more complex to read through. But you'll start to find like all the registers that do different things. And the registers that are the most interesting for you are the I/O registers. And the I/O registers, I think it's always good to go into the index to find them. But let me show it to you there. If we go to the registers, what they are telling us is actually what instructions to switch to tell the computer to do to turn on off the different pins, for example. These things can get easily complex, and so I don't want to go too crazy on it, but I think it's good that you try to navigate through the datasheet, at least to understand how most of it, these 623 pages that you say how long this is, it's mostly just telling us what switches to turn on and off to different operations. So at the end, it's like if I'm giving you a manual for a videotape recorder from the 90s, and I'm just telling you what switches to turn on off to do whatever you want to do with it. However, as switches could be quite complex to turn on off, it's easier that we use libraries that simplify this, as Arduino, where by simply doing a digital write or a digital read, we could actually execute all this complexity. So at the end, when we think about Arduino or other libraries to program microcontrollers, what you are looking at is simply an abstraction of all these pages into code. Now we are talking to code instead of reading code and implementing ourselves things. And why people keeps not implementing things directly into the Arduino language? Why, if you look at some new code, it might look something more as what I'm showing you now on screen, working directly with the registers, working directly with the memory, because this is extremely efficient and is extremely precise on time. So if you want our 3D printer to draw a circle and we need to synchronize 3 motors at the same time, and the time it happens between we actually give an instruction to the motor for the x-axis, it's delay a few microseconds from the one in the y-axis. Instead of a circle, we might get an ellipse. And so that's why it's important to keep things synchronized on time. And for certain occasions, not for all of them, we need to go to that level of complexity where we actually define things by actually using registers, and we go such a low level onto the chip. So I hope these things in a way explain you why datasheets are important and why you need to be able to read them even though you don't understand them fully. And tomorrow in the class, you'll see better how we put them into practice.
Super.
Okay, long class.
I think, guys, at this moment, it would be very interesting. I don't know if you have mentioned this, Guillem. I'm sure that you did, but just to clarify that all these things that we are doing now is what Arduino does at the end. So when we say we are gonna flash make a blink on your LEDs, you are actually calling a function that does exactly the same thing underneath within the Arduino framework. And that is very powerful to know, because then when you understand this type of things, you can use the Arduino itself, but then you can use other things and even edit and do your own Arduino, since it's all open.
Exactly. In fact, what I remember what I said before, linked to what Oscar just said, that in fact, when a new chip is released, for example, before we use the ATtiny 44, and now I show you the datasheet for the ATtiny 1640. So when the guy who coded the library for the digital write that used to work well on the ATtiny 44 wants to know if it's going to work well on this new ATtiny, he could go to the documentation and see if the registers that you need to actually touch to switch the spin on the microcontroller are the same or are new ones. And based on that, he could even know before the chip is actually fully released, and he could test it physically on his workshop if this is going to work or not. And so as Oscar is saying, Arduino is just datasheet make code in a way. Anything else? Any questions? I feel it's been really long. I'm sorry if you are already sleepy from such a long talk, but hopefully it was useful.
Yeah. Well, my opinion, I think that this is a very good session, because it's closing all the things that we have been touching separately in the 3 weeks of electronics. What I'm trying to say is that we've been giving you some little parts of the big picture. You have done your own programmer without really knowing what it was. You have designed your own board without really knowing why to put connections into the chip. You have done, probably some of you have already programmed and followed the different workflows for the different chips that we gave you. But now it's time that you close a little bit the circle and you start thinking, okay, now I understand the whole thing. This is somehow starting to make sense. And the different layers that I have in front of me, now I can start understanding them and controlling them and hacking them somehow. So you can start like doing your own things a little bit more powerful, not just doing basic tutorials, but more advanced things.
Yeah, exactly. I have to say that most of the time what could happen to you actually is that you are not the ones going at the detail fully of a data sheet, but at least telling people they should do so. So it happens to me sometimes working with an engineers, developing something, which is like, guys, don't tell me this is not possible, because if we look there, we might find it. Let's look at data sheet. Let's do a proper analysis. So at the end, what we are telling you is that it's not that you need to be a master of data sheets, but you need to know at least to tell people where to look for the information when you are working and on a project. So this is all for today, at least for my side. Pleasure to be here. And if there's no more questions for me, we can close the class.
Thank you, Guillaume.
Bye-bye.
Thank you.
Have a nice day.
Thank you.
Thank you, Guillaume.
Thank you.
Bye.
Thank you.
Bye-bye.
Pleasure.
Thanks a
Bye-bye.
lot.
With you.
Bye.
Bye.